Hello, everyone, and welcome to the webinar, The Next Wave of Hydrogen Technology. My name is Runil Dalia, Principal Analyst here at Lux Research, and I will be moderating today's session. And presenting today is my colleague, Chansu Dagane, Analyst here at Lux Research. Now, throughout the webinar, you can type any questions you have in the questions box on your screen, and time permitting, we will answer all the questions that we can. If your question does not get answered, please don't hesitate to email it to questions@luxresearchinc.com and we will respond. And if at any point you experience technical difficulties, such as a frozen screen, simply refresh your browser and check that your internet connection is strong. Now, let's jump into the presentation. Chansu, over to you.
Thank you, Runil. Hi, everyone. Welcome again to today's webinar on Next Wave of Hydrogen Technologies. In terms of agenda, today we will take the EU as an example. While the hydrogen economy is a global industry, the EU is one of the most ambitious regions when it comes to establishing a hydrogen economy. So we will briefly discuss its hydrogen strategy, progress, and highlight the challenges it has been facing in meeting these goals. This will bring us to the next generation technologies and how these technologies tie to the EU's decarbonization strategy. Then we will conclude with three key actionable takeaways on these emerging technologies. So let's get started. The EU's energy transition started in 2019 with the launch of the EU Green Deal, which officially committed making the EU's energy, climate, transport, and taxation policies fit for reducing net greenhouse gas emissions by at least 55% by 2030 compared to 1990 levels. The EU's energy transition gained momentum with multiple policy measures around establishing a local hydrogen economy. The EU officially announced its hydrogen strategy in 2020, which set local production and import goals for green hydrogen. In order to ensure demand for this hydrogen, the EU announced a couple of policy acts and directives like the Renewable Energy Directive, mandating the industrial sector to replace 42% of grey hydrogen with green hydrogen by 2030. And to make sure that the price is competitive enough for industrial adoption, the EU held 2 hydrogen bank auctions to subsidize green hydrogen producers. So taking a look at the EU's hydrogen production and import goals, the EU plans to import and produce 10 million tons of green hydrogen by 2030. We are only 5 years away from 2030. So how is the EU doing on this target? The EU produced only 37,000 tons of green hydrogen in 2024. So it has not yet reached 1% of its target by 2030. So despite all the efforts, we can see that the EU is not on track to meet its net zero targets. And why is that? Of course, there are a couple of reasons. And the key reason for falling behind in these targets is the very high production cost today. The independent nonprofit Dutch Research Institute, TNO, conducted a levelized cost of hydrogen strategy by gathering data anonymously from the projects that are under construction in the Netherlands. The results revealed that the cost of production will be around 14 euros per kilogram of hydrogen, with electricity and the capex as the major cost contributors. So if this is the case, in the Netherlands, the production will need to shift to other European countries because no one will be producing or using hydrogen at such a price. The situation is not very different in other European countries. These results are adopted from the European Hydrogen Bank auctions. So it's important to note that these projects have not yet passed the FID. So the estimations that you're seeing here are relatively more optimistic estimates than the previous study. While we have Spain as an exception here, the LCOH still remains prohibitively high to adopt green hydrogen in the EU. So what's the outcome of this situation? So this high production cost led to the cancellation of multiple large-scale hydrogen production and infrastructure projects. And if these projects are not moving forward, are not FIDing and starting construction, the EU will need to rely mostly on hydrogen imports. But several hydrogen projects, hydrogen hubs, large-scale facilities are also being halted outside the EU. So it risks the EU's goal of importing 10 million tons of hydrogen by 2030. And it leaves the EU with local production as the only source of green hydrogen, because these regions will not be exporting hydrogen before their local demand is met. So going back to this figure, if the EU were to produce its own green hydrogen, technology developers would need to focus on two major cost contributors here, which are CapEx and electricity. So CapEx can be lowered by mass production, by increasing stack sizes, and the capacity utilization will be critical. For example, this study assumes 55%, and when the CapEx is high, it's assumed to be around 3,000 euros per kilowatt year. The impact of CapEx becomes much higher than at higher capacity utilizations. So operating close to full capacity will also help reduce the LCOH. When it comes to electricity, the first thing to address is the equipment's performance. It can be improved to lower the overall electricity consumed for hydrogen production. And the second thing that you can do as a producer in the EU is to secure cheap renewable electricity. So lowering the CapEx portion is not necessarily a technical challenge, but the electricity portion is. And this is where we will focus on today. So if we were to reduce the cost of electricity by sourcing cheap renewable electricity in the EU is not a very attractive region. The final electricity price for the European industrial customers is currently around $100 per megawatt, which is much higher than the other regions like US, China, or India. There are some European countries like Norway or France, which can provide relatively cheaper electricity than the EU average. The EU's electricity price still remains uncompetitive. And as you can see from the jump in 2020, the price of electricity is prone to increase due to geopolitical events like wars, because the EU has been relying on energy imports. So, based on everything we have discussed so far, how can the EU ensure energy independency while meeting its decarbonization goals? So the EU will need to prioritize local green hydrogen production, which is produced by water electrolysis. As this market map shows, there is no shortage of technology developers in water electrolysis. There are over 150 companies actively commercializing their electrolysis technologies. But the majority of these technologies you see here, like alkaline, PM, or AEM, they all have the same issue from the perspective of the EU. The issue is that they require a source of electricity, and the EU has expensive electricity. So what if we can find a system that does not consume electricity at all? So what do we mean by that? Let's take a look at the evolution of electrolysis. Based on Lux's taxonomy, traditional alkaline, PM, or AEM technologies are lumped together under the first generation of hydrogen production technologies. The only energy input for these technologies is electricity. And there are many companies active in first generation technologies. If we take ThyssenKrupp as an example, they developed the zero gap alkaline technology, meaning that there is virtually no gap between the separator and the electrodes. So overall, this design results in lower ohmic resistance over across the stack, and it leads to higher efficiencies compared to traditional designs. ThyssenKrupp claims over 82% efficiency based on the high rating value of hydrogen, and this is one of the highest efficiencies claimed in liquid alkaline space. And if we translate this, into the cost of production, the LCOH from ThyssenKrupp's electrolyzer is estimated to be around 5.11 euros per kilogram. This is Lux's estimation, and as you can see the assumptions that went into the calculation under the figure. We assumed an average alkaline capex and 50 euros per megawatt hours of electricity, which is much lower than what the EU can provide today. The electricity consumption is what the company claims to provide with its product. So this estimate represents one of the most optimistic scenarios for the first generation of electrolyzers. And so even with one of the best technologies in the market today, hydrogen will cost over 5 euros per kilogram, which is very expensive. So how can we further improve this LCOH? As you can see, electricity is a major cost contributor here. So we will focus on reducing this portion. And this is where the next generation technologies come into play. These technologies partially replace the need for electricity with thermal energy or other chemical reaction mechanisms. And these approaches include decoupling, leveraging metal oxides, or using microbes. There are a couple of players active in the space, and one of the key players is H2Pro. So what do they do differently with their technology? So they decouple hydrogen and oxygen evolution by using an electrochemically and thermally activated nickel-based anode. So in the first step, unlike a conventional anode, they charge their ETAC anode with hydroxide ions during hydrogen evolution. So this is when you apply an external voltage. And in the second step, electricity is switched off, and this is called the discharging step. And this is when the company introduces a hot electrolyte at 95 degrees Celsius. And this is the temperature at which the ETAC anode gets activated and releases oxygen with no external voltage applied. So the company eliminates the need for electricity for the oxygen evolution. And they have been working on piloting the first generation of this technology, and they target an electricity consumption of 44 kilowatt hours per kilogram of hydrogen by 2030. In the second generation, there are also other concepts involving the use of microbes to break biomass from agriculture, forestry, paper recycling, and so on, into hydrogen and CO2 at temperatures typically below 50 degrees Celsius. These companies typically differentiate by the microbes they use in their process, but this process is called the microbial electrolysis, and this has been at the lab scale for years due to low hydrogen yield and challenges in scaling up with microbes, because microbes are difficult to monitor at scale. But we have identified one company, Key Hydrogen, that does not use microbes in their biomass electrolysis process. What they developed is a pure electrochemical looping system using a liquid catalyst medium. So they introduce the biomass slurry in this metal reactor on the right hand side in the picture here. This biomass slurry reduces the catalyst and releases CO2. Then the reduced catalyst gets oxidized in the electrochemical cell on the left to regenerate the catalyst, but also to produce hydrogen. And we mentioned that they're not using any microbes, so that's one differentiation. The other differentiator is that the biomass never enters the electrochemical cell, so CO2 and hydrogen evolve in different reactors. So the generation of these gases are also decoupled. And as a result, the company claims to require about 50 kilowatt hours per kilogram of hydrogen. And you can see the output ratio is 9:1. This is an improvement to biomass electrolysis technology overall, and it's worth keeping an eye on the performance results as the company moves out of the lab, because the output is biogenic CO2 and hydrogen, which can be used to produce various low carbon fuels and chemicals. If we take a look at the economics of the second generation, for this analysis, we picked H2Pro's technology because it's currently the most advanced in the market. As we mentioned, it doesn't require electricity for oxygen evolution, which has, a high Hoover potential and requires 4 electron transfer. And for the sake of this analysis, for the sake of the comparison with the Gen 1, with the first generation, we assumed the capex, the same capex as ThyssenKrupp. And as we can see here, with a second generation electrolyzer that is more efficient, it is possible to save on the cost of electricity as well as the capex, because if 2 electrolyzers cost the same amount of money, but one is more efficient, then the price you pay per kilogram will be lower with the more efficient. And this is what we are seeing here. Overall, with the second generation of electrolyzers, the cost is reduced by about 30 cents per kilogram. So what if we went one step further and wanted to eliminate the need for electricity completely? This is when we would be pursuing the third generation of technologies, which don't require any grid connection or renewable energy infrastructure development to produce hydrogen. These technologies include thermochemical water splitting and photolysis. And in terms of a key player here, in the third generation space, we have utility. They eliminate the need for external electricity by oxidizing carbon monoxide-rich industrial off-gases, like from a steel plant, or hydrocarbon fuels like methane, biogas, etc., at the anode of its electrolyzer. So it uses an external heat source, like a boiler, to get its reactor running at 600 degrees Celsius. Then it oxidizes, it introduces the off-gases or other types of hydrocarbon fuels at the anode to produce heat, to maintain the temperature, and also to provide electrons to the cathode reaction. And the anode and the cathode are separated with an ion-conducting electrolyte membrane that transfers oxygen ions from cathode to the anode, like a traditional solid oxide cell. But the membrane also has a second function, which is to transfer electrons from anode to cathode, because there is no external circuit here, unlike the traditional electrolyzers. So you can imagine that, the anode side is operating like a fuel cell, and the cathode splits water into hydrogen and oxygen. So, by doing so, the company does not require any electricity. They recently piloted the technology in Canada, and it's working on commercializing it with other industry players like ArcelorMittal, and it primarily targets the steelmaking sector. And it's a retrofit solution for existing steel facilities, so it's possible to adapt without major changes to existing facilities. Photolysis is another concept. It's an early stage technology, and the concept refers to using light-sensitive photocatalysts to facilitate water splitting, and the sun acts as the energy source for this reaction. So the sun generates the electrons that are needed for water splitting. This is not a new concept, but it has failed to reach commercialization for decades, mainly due to the low solar to hydrogen efficiency. We have one company, Sun Hydrogen, which has been developing a technology since 2009, and it uses these photoelectro-synthetically active nanostructures with multiple layers of oxidation and reduction catalysts. The company assembles these these units into larger panels, and the largest panel it has tested so far is a 1,200 meter square panel. And this was a scale up from a 100 centimeter square panel, which demonstrated 10.8% solar to hydrogen efficiency. So the company is now preparing to scale up to about 1.92 meter square panel size. But as we have seen from its recent scale up, the company was not able to maintain its solar to hydrogen efficiency, and it actually went lower than the 100 meter square panel. So with the scale up, it is the key for company success will be first maintaining and then possibly improving its solar to hydrogen efficiency. Because back in 2021, we know that the company claimed 3 times higher solar to hydrogen efficiency than the market average, which is, let's say, 10%. But as we can see here, the company is not able to demonstrate this efficiency as it tries to scale up. So low efficiency is still a barrier to adoption of photolysis, and it will likely take many years for this technology to become a commercially proven technology. So we took utility as an example here to show you, what the impact of eliminating electricity from the system would look like. But please keep in mind that even though you don't need electricity for water splitting, you would still need some electricity for the balance of plant components like compressors and pumps to run the system. And based on data available, you can see that you could produce hydrogen at around 2.66 euros per kilogram. And this is a vast improvement compared to ThyssenKrupp's technology, which was at around 5 euros per kilogram. So you can see the evolution of electrolysis here. With every generation, you're eliminating a portion of the cost of electricity. From Gen 1 to Gen 2, the cost of production improves by saving on electricity, but the big improvement is really when you completely eliminate the electricity. But please keep in mind that you are eliminating the electricity, you're not eliminating the energy consumption. So there's still a theoretical minimum energy required for water splitting the electricity with something else, which could be thermal energy in the case of utility or solar energy in the case of sun hydrogen. So to recap, moving from Gen 1 to Gen 2 and Gen 3, many companies are already active in this space, right? We have many companies actually actively commercializing Gen 2 and Gen 3 technologies, and we have seen that some companies are already moving out of the lab. And as we have seen earlier, moving to third generation of technologies significantly reduces the cost of production. But the question is, what is the ideal cost of hydrogen to enable industry adoption? And what do these technologies mean for the EU? So when it comes to industrial adoption, regardless of the electrolyzer technology you plan to use, these are the main industrial applications that you would need to target. And in these applications, hydrogen competes not only with the fossil incumbents, but also with emerging alternatives or alternative decarbonization solutions like direct electrification. So, the criticality of hydrogen and willingness to pay for green hydrogen will be different from an application to application and from region to region. For the EU, the industrial applications take the priority. And as we mentioned earlier, it targets replacing at least 42% of gray hydrogen used in industry with green hydrogen by 2030. And as we have seen, the EU is not on track to meet these binding targets because it's not producing at the scale it needs to produce. So what's the price of hydrogen that would allow the EU to meet its targets? Based on our analysis, these are the break-even green hydrogen prices for major industrial and mobility applications. And as you can see here, most of these applications require hydrogen at below $3 per kilogram, which can only be produced by a third generation technology. And this is why the EU needs next generation technologies. So to wrap up what we have discussed so far, traditional electrolyzers are currently the only commercial technology available for large-scale deployments today. So by 2030, these technologies will dominate the deployment activity, but we have seen that they lead to very high production costs. So the first of a kind large-scale deployments of these traditional electrolyzers will require significant financial support from the governments through the grants, but in the long term, the second generation and the third generation technologies like decoupling and thermochemical water splitting will take over some of the share from the conventional electrolyzers, and these technologies should be considered for piloting today to understand how they can be further improved and be ready for commercial deployments after 2030. We have seen that photolysis and biomass electrolysis can also demonstrate a reduction in the cost of electricity, but these technologies are not ready for adoption due to technological challenges that we have discussed earlier. So we recommend waiting for these technologies to mature beyond lab scale to engage. And as with any early stage technology, the interest from industrial players that are already producers or consumers of hydrogen will drive the commercialization of these technologies. Right now, there are a few corporations partnering with startups in second generation and third generation on pilot projects, but the corporate involvement will need to grow to finance more projects. So with that, I would like to thank everyone for their attention, and we can move on to the Q&A session.
Great. Thank you very much, Chansu, for this presentation. This was really enlightening. And as I mentioned earlier, we will now be taking questions that you may have on the presentation, which you can type in the questions box. And again, if we don't get to your question on this call, then someone from Lux will be in touch right after the webinar. But I see that a couple of questions came in already, Chansu. And I see there's a couple of questions on technologies, and I try to put the questions together into a single one. But essentially, the nature of the questions is really around the evolution of these technologies, because you talked about Gen 1, Gen 2, Gen 3 electrolyzer technology. But how do you see the landscape of electrolysis evolving? Do you see Gen 1 technologies being deployed in the near term, followed by Gen 2, followed by Gen 3, and then these technologies will get replaced by the more advanced generation? Or do you think that in the future it will be a mix of Gen 1 and Gen 2 and Gen 3 electrolysis technologies?
Thank you, Neil, for the question. We think that there will be a mix of technologies. It's because this presentation was focusing on the perspective of the EU, and EU has expensive electricity, and we think that the EU might be better off using thermal-driven approaches rather than pure electrochemical systems for green hydrogen. But if we consider, Chile, Saudi Arabia, or parts of Africa, these regions have cheap electricity. So the first generation technologies could also be considered, could also be viable in these regions. And other than the regional aspect of it, we also have the application side of things. So it will also depend on the applications, right? For example, utility system, it uses off gases. So it's a good fit for, it's a good fit to decarbonize steel making, but it's not a good fit for all industrial applications because they require, a minimum threshold, like minimum 15% carbon monoxide concentration in the off gas they use. So for, other industrial applications, mobility or chemicals production, we could also consider low temperature first generation or second generation technologies. So there is no one solution for all applications. So there will be a mix in the future.
In the future, okay. All right. Another question I have is, and this is more specifically around Gen 1 technology, and that's a question that came in around ThyssenKrupp, because you introduced ThyssenKrupp as, I think it was a 60% efficiency, and it has one of the more advanced systems in Gen 1 electrolysis. Is that it when it comes to, innovation in Gen 1, or do you see the performance of Gen 1 technology, being pushed even further than the ThyssenKrupp system?
Yeah, another great question. Thank you for asking. So we mostly talked about the traditional liquid alkaline, and ThyssenKrupp, as you mentioned, has one of the most efficient technology in the market with over 82% claimed efficiency. But there are exceptions, right? So we have Hysata, for example, from Australia, and their technology is the exception in the first generation of technologies, because their technology only consumes electricity, but it does not operate the way liquid alkaline technologies do. So what they do differently is that they build the so-called capillary fed electrolyzers, where hydrogen and oxygen evolve without any bubble formation. So the company completely eliminates the inefficiencies caused by this, bubble resistance that we typically see in liquid alkaline, and the lack of bubbles, also eliminates the excess heat generation in the system, which allows for self-cooling. So it also simplifies the balance of plant. And with all of these, the company claims a 95% system efficiency, which is slightly higher than ThyssenKrupp's technology. But of course, the company is working on commercializing. So it is working on a 5 megawatt system. Even though it has higher efficiency, it is not able to provide the same scale stacks as ThyssenKrupp. So it's good to keep in mind the current scale of the technology as well.
Right. Okay, perfect. All right. There's a few more questions that came in while you were answering the first two, but unfortunately, that's all the time that we have today. But of course, we will get back to you with regards to this question. So this really concludes our webinar for today. The slide presentation and the recording from this webinar will be sent to all attendees via email. And after leaving the webinar, you will be prompted to complete a survey onto this presentation, and we will really appreciate any feedback that you may have that really helps us inform and improve future webinars. And in the meantime, take a moment and check out our upcoming webinars. And for now, thank you for joining us, and have a great day. Thank you very much.
Thank you.